Question 1. Cost-benefit analysis shows that constructing a new ethanol production facility offers significant economic advantages, but the project team is debating the most critical factor for successful implementation under the Certified Renewable Energy Professional (CREP) regulatory framework. Which of the following approaches is paramount to ensuring the project's long-term viability and regulatory compliance? Option A. Prioritizing the immediate economic returns by fast-tracking construction and deferring detailed environmental and feedstock sustainability reviews until after the facility is operational and generating revenue. Option B. Focusing primarily on meeting the minimum biofuel blending mandates set by the regulatory body, without extensive investigation into the specific quality and performance standards of the blended fuel beyond basic compliance. Option C. Maximizing the facility's production capacity by sourcing the cheapest available feedstock, assuming that any environmental concerns can be addressed through minor operational adjustments post-construction. Option D. Conducting a comprehensive environmental impact assessment that includes detailed analysis of feedstock sourcing sustainability, water usage, air emissions, and waste management, with proposed mitigation strategies aligned with all relevant environmental regulations and biofuel standards. Correct answer is D. Conducting a comprehensive environmental impact assessment that includes detailed analysis of feedstock sourcing sustainability, water usage, air emissions, and waste management, with proposed mitigation strategies aligned with all relevant environmental regulations and biofuel standards. Explanation. Scenario analysis. This scenario presents a common implementation challenge in the renewable energy sector, balancing the economic benefits of a new biofuel production facility with its potential environmental and regulatory compliance obligations. The challenge lies in navigating the complex web of regulations governing biofuel production, feedstock sourcing, emissions, and waste management, while also ensuring the project remains economically viable. Professionals must exercise careful judgment to avoid costly penalties, reputational damage, and project delays. Correct approach analysis. The correct approach involves a comprehensive environmental impact assessment, IA, that rigorously evaluates potential risks and proposes mitigation strategies aligned with the specified regulatory framework. This approach is correct because it proactively identifies and addresses potential environmental issues before they become significant problems. It ensures compliance with all relevant environmental laws and standards, such as those pertaining to water quality, air emissions, and land use, as mandated by the regulatory body overseeing renewable energy projects. This thorough due diligence demonstrates a commitment to sustainable development and responsible corporate citizenship, which are often implicit or explicit requirements in professional conduct and industry best practices. Incorrect approaches analysis. Focusing solely on the economic benefits and assuming regulatory compliance will be a minor hurdle is an incorrect approach. This overlooks the stringent environmental standards and permitting processes that are integral to renewable energy projects. It risks significant delays, fines, and potential project cancellation if unforeseen environmental impacts are discovered during later stages, or if the facility fails to meet mandated biofuel standards. Prioritizing the use of the cheapest available feedstock without a thorough assessment of its environmental footprint and sustainability certifications is also incorrect. Many jurisdictions have specific regulations regarding the sustainability of biofuel feedstocks, including criteria for land use change, biodiversity impact, and greenhouse gas emissions associated with cultivation and harvesting. Failure to comply with these feedstock standards can invalidate the biofuel's eligibility for incentives and lead to non-compliance with blending mandates. Implementing a biofuel blending strategy that meets the minimum mandated percentage but neglects the quality and performance standards of the blended fuel is another incorrect approach. Biofuel standards often encompass not only the composition of the biofuel itself, but also its compatibility with existing infrastructure and engines, as well as its performance characteristics. Blending fuels that do not meet these standards can lead to engine damage, reduced efficiency, and potential liability issues, in addition to failing to meet the spirit and intent of the blending regulations. Professional reasoning. Professionals in the renewable energy sector must adopt a holistic approach that integrates economic, environmental, and regulatory considerations from the outset. This involves 1. thoroughly understanding and adhering to all applicable regulatory frameworks, including environmental protection laws, biofuel production standards, and blending mandates. 2. Conducting comprehensive EIAs to identify and mitigate potential environmental risks. 3. Carefully selecting feedstocks based on sustainability criteria and regulatory compliance. 4. Ensuring that all biofuel products meet established quality and performance standards. 5. Engaging with regulatory bodies proactively to ensure smooth permitting and compliance. This systematic process minimizes risks, maximizes project success, and upholds professional integrity. Question 2. The control framework reveals a client eager to expedite the installation of a new rooftop photovoltaic (PV) system to take advantage of current incentives. They have proposed sourcing some components from a less reputable supplier, citing significant cost savings, and have also suggested that the installation team bypass certain steps outlined in the PV module manufacturer's installation manual to accelerate the process. As a certified renewable energy professional CREP, what is the most appropriate course of action? Option A. Advise the client that all PV modules and balance of system components must be certified by a recognized testing laboratory, and that the installation must strictly follow the manufacturer's guidelines and all applicable electrical codes to ensure safety and system longevity. Option B. Proceed with the installation using the less reputable supplier's components, but inform the client that this deviates from standard practice and may impact system performance and warranty. Option C. Recommend using the less reputable supplier's components, but insist on adhering strictly to the manufacturer's installation manual to mitigate potential risks associated with the components. Option D. Agree to use the less reputable supplier's components and instruct the installation team to follow the client's suggested shortcuts to meet the expedited timeline and cost objectives. The correct answer is A. Advise the client that all PV modules and balance of system components must be certified by a recognized testing laboratory, and that the installation must strictly follow the manufacturer's guidelines and all applicable electrical codes to ensure safety and system longevity. Explanation: this scenario presents a professional challenge because it requires the certified renewable energy professional CREP to balance the client's desire for immediate cost savings with the imperative to adhere to established safety and performance standards for PV system design and installation. The pressure to expedite installation without compromising quality or compliance can lead to shortcuts that have significant long-term consequences, including system failure, safety hazards, and regulatory noncompliance. Careful judgment is required to identify and mitigate these risks. The correct approach involves prioritizing the use of certified components and ensuring that the installation strictly adheres to the manufacturer's guidelines and relevant national electrical codes. This ensures the system's safety, reliability, and optimal performance over its lifespan. Regulatory justification stems from the fundamental requirement to design and install electrical systems in a manner that prevents hazards to life and property, as mandated by codes such as the National Electrical Code, NEC, in the U.S. Ethical justification lies in the professional's duty to act in the best interest of the client and the public by delivering a safe and effective system. An incorrect approach that suggests using readily available, uncertified components to reduce upfront costs fails to meet regulatory requirements for component certification and safety. This bypasses essential quality control measures designed to ensure the component's performance and safety under operational conditions, potentially leading to premature failure, fire hazards, or electric shock. Another incorrect approach that advocates for deviating from manufacturer installation instructions to speed up the process is also professionally unacceptable. Manufacturers' instructions are developed based on extensive testing and are crucial for ensuring the correct and safe operation of the equipment. Deviating from these instructions can void warranties, compromise system performance, and create safety risks, violating both regulatory mandates for proper installation and ethical obligations to the client. Professionals should employ a decision-making framework that begins with a thorough understanding of project requirements, client expectations, and all applicable regulations and standards. This involves a risk assessment to identify potential deviations from best practices and their consequences. When faced with pressure to compromise on quality or compliance, the professional must clearly communicate the risks and regulatory implications to the client, advocating for the correct, compliant approach. If the client insists on non-compliant methods, the professional must be prepared to withdraw from the project to uphold their ethical and regulatory obligations. Question 3. Risk assessment procedures indicate a potential for significant avian mortality at a proposed horizontal axis wind turbine (HOT) site due to the turbine's proximity to a known migratory bird corridor. Which of the following approaches best addresses this identified risk in accordance with professional ethical obligations and regulatory frameworks for renewable energy development? Option A. Prioritize maximizing the turbine's energy generation efficiency by ensuring continuous operation at optimal speeds, as this contributes to the overall renewable energy targets. Option B. Implement operational adjustments such as blade pitch control modifications and temporary curtailment during peak migration periods, informed by a detailed site-specific avian impact study. Option C. Rely on general industry statistics regarding avian collisions with HOT to conclude that the risk is within acceptable limits without further site-specific investigation. Option D. Recommend the installation of a vertical axis wind turbine, VAWT, instead of the HOT, assuming VAWT inherently pose a lower risk to avian populations, thereby negating the need for detailed impact assessment. The correct answer is B. Implement operational adjustments such as blade pitch control modifications and temporary curtailment during peak migration periods, informed by a detailed, site-specific avian impact study. Explanation: Scenario analysis. This scenario is professionally challenging because it requires a renewable energy professional to balance the operational efficiency of a wind turbine with potential environmental impacts, specifically concerning avian populations. The challenge lies in interpreting and applying regulatory guidelines that may not always provide explicit quantitative thresholds for acceptable risk, necessitating a nuanced judgment based on best practices and available scientific data. The professional must consider the specific characteristics of the turbine HOT vs VAWT, its components and its operational parameters, e.g., blade design, pitch control, in relation to the local ecosystem. Correct approach analysis. The correct approach involves a comprehensive, site-specific risk assessment that prioritizes mitigation strategies for identified avian collision risks. This aligns with the ethical responsibility of renewable energy professionals to minimize negative environmental externalities, as often mandated by environmental protection regulations and industry best practices. Such an assessment would consider factors like turbine height, rotor swept area, blade visibility, operational speed, and local bird migration patterns. The professional would then recommend specific, evidence-based mitigation measures, such as curtailment during peak migration periods, deterrent technologies, or habitat management, all within the framework of relevant environmental impact assessment guidelines. This proactive and data-driven approach ensures compliance with regulatory objectives for sustainable energy development. Correct approach is analysis, an approach that solely focuses on maximizing turbine efficiency without considering avian impact fails to meet regulatory and ethical obligations. Environmental regulations typically require developers to assess and mitigate potential harm to wildlife. Ignoring this aspect constitutes a failure to adhere to due diligence and could lead to regulatory penalties and reputational damage. An approach that relies on generic, non-site-specific data for risk assessment is also flawed. While general information on turbine-avian interactions is useful, each wind farm site has unique ecological characteristics. Failing to conduct a site-specific assessment means potential risks specific to that location might be overlooked, leading to inadequate mitigation strategies and non-compliance with environmental impact assessment requirements. An approach that dismisses potential avian risks based on the turbine type, e.g., assuming VAWT are inherently safe, without a proper assessment is a significant ethical and regulatory failure. While VAWT may present different risk profiles than HOT, they are not risk-free. A professional must evaluate all turbine types based on empirical data and site-specific conditions, not on generalized assumptions. Professional reasoning. Professionals in this field must adopt a risk-based decision-making process that integrates technical expertise with environmental stewardship. This involves 1. Identifying potential risks, understanding how turbine design HOT vs VAWT components and operational parameters can interact with the environment. 2. Assessing the likelihood and severity of risks, utilizing site-specific data and scientific literature to quantify potential impacts. 3. Evaluating mitigation options, exploring a range of strategies to reduce identified risks. 4. Implementing and monitoring, deploying chosen mitigation measures and continuously evaluating their effectiveness. 5. Regulatory compliance, ensuring all actions align with applicable environmental laws, regulations, and permitting conditions. This systematic approach ensures that the pursuit of renewable energy goals is conducted responsibly and sustainably. Question 4. The assessment process reveals that a proposed solar farm site experiences significant seasonal variations in atmospheric clarity and is subject to localized terrain-induced shading patterns. Which approach to solar resource assessment best aligns with professional standards for accuracy and regulatory compliance for a certified renewable energy professional CREP? Option A. Extrapolating solar radiation values from a geographically distant location with similar latitude but different climatic and topographical features. Option B. Employing site-specific meteorological data, accounting for local atmospheric attenuation, and using sun path diagrams to model irradiance on the proposed module orientation throughout the year. Option C. Utilizing generalized extraterrestrial radiation data and applying a standard air mass correction factor without accounting for local atmospheric conditions or shading. Option D. Relying on a single, uncalibrated pyranometer reading taken at solar noon on a clear day to represent the entire year's solar resource. The correct answer is C. Utilizing generalized extraterrestrial radiation data and applying a standard air mass correction factor without accounting for local atmospheric conditions or shading. Explanation. The assessment process reveals a common challenge in renewable energy project development, accurately characterizing the solar resource for a specific site. Professionals must navigate the complexities of solar geometry, atmospheric effects, and data interpretation to provide reliable resource assessments. This scenario is professionally challenging because an inaccurate assessment can lead to significant financial underperformance or overestimation of a project's viability, impacting investor confidence and regulatory compliance. Careful judgment is required to select the most appropriate methods and data sources. The correct approach involves utilizing site-specific solar radiation data, considering atmospheric conditions relevant to the project's location, and applying appropriate models to account for factors like air mass and solar angles. This aligns with professional standards for resource assessment, which emphasize accuracy and defensibility. Regulatory frameworks for renewable energy projects, such as those overseen by the Certified Renewable Energy Professional (CREP) standards, mandate that resource assessments be based on sound scientific principles and reliable data to ensure that project performance projections are realistic and achievable. This approach ensures that the assessment is robust, transparent, and can withstand scrutiny from regulators and stakeholders. An incorrect approach would be to rely solely on generalized solar radiation databases without considering local atmospheric conditions or site-specific shading. This fails to account for the variability of the solar resource due to factors like cloud cover, aerosols, and humidity, which can significantly impact actual energy yield. Ethically, this is a failure to exercise due diligence and provide a professional, accurate assessment. Another incorrect approach is to ignore the impact of solar angles and sun path diagrams on irradiance at the module plane. While the solar constant represents extraterrestrial radiation, the actual radiation reaching a solar panel is heavily influenced by the angle of incidence, which changes throughout the day and year. Failing to incorporate this leads to an incomplete and misleading assessment, violating the professional obligation to provide a comprehensive analysis. A third incorrect approach is to use data from a pyranometer without understanding its limitations or calibration status, or to use pyrheliometer data inappropriately for diffuse radiation. Each instrument measures different components of solar radiation, and misapplication or reliance on unverified data can lead to significant errors in resource assessment, undermining the credibility of the project proposal and potentially violating CREP ethical guidelines regarding competence and accuracy. Professionals should employ a decision-making framework that prioritizes data integrity, methodological rigor, and site specificity. This involves understanding the limitations of different data sources and measurement instruments, critically evaluating the assumptions underlying any modeling, and ensuring that the final assessment is transparent and well documented. When faced with uncertainty, professionals should err on the side of conservatism and clearly communicate any assumptions or limitations to stakeholders. Question 5. The efficiency study reveals that a proposed offshore wind farm's projected energy output is lower than initially anticipated due to unforeseen seabed conditions impacting turbine foundation stability and increased wake effects from suboptimal turbine spacing. Which of the following represents the most professionally responsible course of action under U.S. regulatory frameworks for offshore wind development? Option A. Proceed with the original design. Assuming minor operational adjustments can compensate for the seabed issues and wake effects, and focus on maximizing immediate cost savings. Option B. Prioritize cost-cutting measures by selecting less robust foundation solutions and compromising on environmental monitoring protocols to offset the projected revenue shortfall. Option C. Conduct a comprehensive reevaluation of the farm's design and operational parameters, exploring alternative foundation solutions and optimizing turbine spacing to ensure technical integrity, environmental compliance, and economic viability within the established U.S. regulatory framework. Option D. Significantly reduce the number of turbines to mitigate wake effects without a thorough reassessment of the project's overall economic viability and renewable energy contribution. The correct answer is C. Conduct a comprehensive reevaluation of the farm's design and operational parameters, exploring alternative foundation solutions and optimizing turbine spacing to ensure technical integrity, environmental compliance, and economic viability within the established U.S. regulatory framework. Explanation. The efficiency study reveals that a proposed offshore wind farm's projected energy output is lower than initially anticipated due to unforeseen seabed conditions impacting turbine foundation stability and increased wake effects from suboptimal turbine spacing. This scenario is professionally challenging because it requires balancing economic viability with robust environmental stewardship and adherence to stringent regulatory requirements for offshore development. The CREP professional must navigate complex technical, environmental, and legal considerations to ensure the project's long-term success and compliance. The correct approach involves a comprehensive reevaluation of the farm's design and operational parameters, prioritizing compliance with the relevant U.S. regulatory framework for offshore wind development, including but not limited to the Bureau of Ocean Energy Management, BOEM, regulations, and relevant environmental protection laws. This reevaluation must specifically address the identified seabed challenges by exploring alternative foundation designs or mitigation strategies that meet engineering standards and environmental impact assessments. Furthermore, it necessitates a thorough review of turbine spacing to minimize wake losses, while adhering to BOEM spatial planning guidelines and any applicable marine spatial planning initiatives. Economic implications of these adjustments must be assessed against the project's overall feasibility, ensuring that any proposed solutions are both technically sound and economically sustainable within the established regulatory and environmental constraints. This approach upholds the CREP ethical obligation to promote responsible renewable energy development by ensuring projects are technically robust, environmentally responsible, and legally compliant. An incorrect approach would be to proceed with the original design, assuming minor adjustments to operational parameters can compensate for the seabed issues and wake effects. This fails to address the fundamental engineering challenges and regulatory requirements for foundation integrity and environmental impact mitigation. It also disregards the potential for increased operational and maintenance costs due to unforeseen foundation issues, jeopardizing the project's economic viability and potentially leading to non-compliance with BOEM safety and environmental standards. Another incorrect approach would be to significantly reduce the number of turbines to mitigate wake effects without a thorough reassessment of the economic viability and the project's contribution to renewable energy targets. This might lead to a project that is technically sound, but no longer economically competitive or impactful, potentially failing to meet the objectives of renewable energy incentives and regulatory approvals. It also overlooks the opportunity to optimize turbine placement and technology to maximize output within the given constraints. A third incorrect approach would be to prioritize cost-cutting measures by selecting less robust foundation solutions or compromising on environmental monitoring protocols to offset the projected revenue shortfall. This directly violates ethical principles and regulatory mandates that require the highest standards for environmental protection and operational safety in offshore developments. Such an approach could lead to significant environmental damage, regulatory penalties, and reputational damage. Professionals should adopt a systematic decision-making process that begins with a thorough understanding of the identified technical challenges and their potential environmental and economic consequences. This involves consulting relevant U.S. regulations, industry best practices, and expert advice. The process should then involve exploring a range of technically feasible and environmentally responsible solutions, assessing their compliance with all applicable laws and guidelines, and evaluating their economic implications. Transparency with stakeholders and regulatory bodies throughout this process is crucial. Question 6. Market research demonstrates a significant demand for small-scale renewable energy projects in a remote, ecologically sensitive watershed. A developer proposes a run-of-river microhydro system, citing its minimal footprint and potential for clean energy generation. However, local environmental advocacy groups have raised concerns about potential impacts on endangered fish species and downstream water flow variability. As a CREP professional overseeing the project's environmental compliance and design review, you are presented with two options. Proceed with the design based on the developer's preliminary environmental assessment, which suggests negligible impact, or insist on a comprehensive, independent environmental impact study before finalizing the design and proceeding with installation. Option A. Proceed with the design based on the developer's preliminary environmental assessment, assuming their findings are accurate. Option B. Insist on a comprehensive, independent environmental impact study before finalizing the design and proceeding with installation. Option C. Expedite the design and installation process by relying on general best practices for microhydro systems, as specific site data is costly to obtain. Option D. Recommend a scaled-down version of the project without a formal environmental impact study, based on the assumption that smaller projects inherently have minimal impact. The correct answer is B. Insist on a comprehensive, independent environmental impact study before finalizing the design and proceeding with installation. Explanation. This scenario presents a professional challenge due to the inherent conflict between maximizing project profitability and adhering to environmental stewardship principles, particularly when dealing with sensitive aquatic ecosystems. The Certified Renewable Energy Professional CREP designation implies a commitment to ethical conduct and regulatory compliance. The decision-maker must balance economic incentives with the legal and ethical obligations to minimize environmental harm, as mandated by relevant renewable energy regulations and environmental protection laws. The correct approach involves prioritizing a thorough, independent environmental impact assessment (IA) that considers the cumulative effects of the proposed microhydro system on the local watershed, including fish migration, water quality, and riparian habitats. This aligns with the precautionary principle often embedded in environmental regulations, requiring proactive identification and mitigation of potential harm before project approval. Ethically, it demonstrates a commitment to sustainable development and responsible resource management, upholding the CREP professional integrity. Regulatory frameworks typically require such assessments for projects that could impact natural resources. An incorrect approach would be to rely solely on the developer's preliminary environmental report, especially if it appears to downplay potential negative impacts or lacks independent verification. This could lead to regulatory noncompliance if the report is found to be insufficient or misleading, and it ethically compromises the professional by prioritizing expediency over thorough due diligence. Such an approach risks significant environmental damage and potential legal repercussions. Another incorrect approach is to proceed with the installation based on anecdotal evidence of minimal impact from similar, but not identical, projects. While past experience can be informative, each site has unique ecological characteristics. Failing to conduct a site-specific EIA is a regulatory failure and an ethical lapse, as it bypasses established protocols designed to protect the environment. This approach neglects the specific requirements for assessing the unique environmental context of the proposed microhydro system. Finally, an incorrect approach would be to delay or ignore concerns raised by local environmental groups or regulatory agencies regarding potential impacts. This demonstrates a lack of professional integrity and a disregard for due process. Ethically, it is a failure to engage constructively with stakeholders and to uphold the spirit of environmental protection laws. Regulatory bodies often consider stakeholder input during the approval process, and ignoring such concerns can lead to project delays or outright rejection. Professionals should adopt a decision-making framework that begins with understanding all applicable regulatory requirements, including environmental permitting and impact assessment mandates. This should be followed by a commitment to ethical principles, such as transparency, due diligence, and environmental responsibility. When faced with conflicting interests, the professional should seek independent expert advice, engage in open communication with all stakeholders, and prioritize decisions that ensure long-term sustainability and compliance. Question 7. The performance metrics show that a proposed hydropower project's energy generation potential is highest with a Francis turbine operating at its optimal head and flow. However, the project site is located in a river system with significant migratory fish populations and is subject to stringent FERC licensing requirements that mandate specific fish passage mitigation measures and habitat protection. Considering these regulatory constraints, which approach best aligns with the Certified Renewable Energy Professional CREP responsibilities under U.S. law? Option A. Proceed with the Francis turbine, assuming that standard fish passage technologies can be retrofitted or are sufficient to meet licensing requirements, prioritizing the highest theoretical energy output. Option B. Conduct a detailed environmental impact assessment to evaluate the suitability of Kaplan turbines, which are known for their adaptability to varying flow conditions and lower fish mortality rates, and ensure the intake structure and powerhouse design incorporate all mandated environmental mitigation features. Option C. Focus on optimizing the penstock design for maximum hydraulic efficiency, deferring detailed environmental compliance considerations to the construction phase. Option D. Select the Pelton turbine due to its simplicity and lower initial cost, and address any environmental concerns only if they arise during the operational phase. The correct answer is A. Proceed with the Francis turbine, assuming that standard fish passage technologies can be retrofitted or are sufficient to meet licensing requirements, prioritizing the highest theoretical energy output. Explanation. This scenario is professionally challenging because it requires a CREP to balance the technical requirements of a hydropower project with the stringent regulatory compliance mandated by the U.S. framework, specifically focusing on environmental impact assessments and permitting for turbine selection and plant design. The core challenge lies in ensuring that the chosen turbine type and associated infrastructure not only meet operational efficiency goals, but also adhere to the environmental protection mandates and licensing conditions set forth by relevant U.S. agencies. The correct approach involves a comprehensive review of the project's Environmental Impact Assessment (IA) and the specific licensing conditions stipulated by the Federal Energy Regulatory Commission, FERC, or equivalent state environmental agencies. This approach prioritizes compliance with regulations governing fish passage, water quality, and habitat protection, which directly influence the selection of turbine types e.g., favoring Kaplan turbines for their ability to operate efficiently across a wider range of flow conditions and minimize fish impingement compared to Francis or Pelton turbines in certain environments. It also ensures that intake structures are designed to mitigate environmental harm, and that powerhouse design considers factors like noise pollution and visual impact as per regulatory guidelines. This is the professionally sound and ethically responsible path, because it directly addresses the legal obligations and environmental stewardship expected of renewable energy professionals in the U.S. An incorrect approach that focuses solely on maximizing energy output without considering regulatory constraints would fail to meet the legal requirements for project approval and operation. For instance, selecting a turbine type based purely on peak efficiency as specific head and flow, without assessing its environmental impact on aquatic life or its compliance with fish passage requirements, would violate FERC licensing conditions and environmental laws like the Endangered Species Act. Another incorrect approach, prioritizing the lowest initial capital cost for penstock materials without evaluating their long-term environmental durability and potential for leakage or contamination, would disregard regulations concerning water quality and potential environmental remediation liabilities. Similarly, designing a powerhouse without incorporating mandated noise reduction measures or visual screening, as often required by local zoning and environmental permits, would lead to non-compliance and potential project delays or fines. Professionals should employ a decision-making framework that integrates regulatory compliance from the outset of project planning. This involves early and continuous engagement with regulatory bodies, thorough environmental impact assessments, and a systematic evaluation of all project components against applicable U.S. federal and state laws and guidelines. The process should prioritize understanding and fulfilling all permitting requirements before finalizing design choices, ensuring that technical feasibility and economic viability are pursued within a robust legal and ethical framework. Question 8. The audit findings indicate that a proposed hydropower project's environmental impact assessment, IA, for a river system in the United States has primarily focused on the projected energy output and the structural integrity of the dam, with limited consideration for the downstream effects on water quality and aquatic habitats. Which of the following approaches best aligns with the regulatory framework for renewable energy projects in the U.S., ensuring comprehensive environmental stewardship? Option A. Implement a post-construction monitoring program for key environmental indicators, with the understanding that any significant negative impacts can be addressed through reactive measures rather than proactive, detailed assessment during the planning and design phases. Option B. Expedite the permitting process by relying on generic environmental impact data from similar hydropower projects, assuming that the impacts will be comparable and manageable without site-specific detailed hydrological and ecological studies. Option C. Focus on optimizing reservoir storage capacity for maximum power generation, with a secondary consideration for environmental impacts only if explicitly mandated by a specific permit condition, rather than as an integral part of the initial assessment. Option D. Prioritize a detailed analysis of the hydrological cycle and river flow dynamics to inform dam design and reservoir operation, explicitly assessing potential impacts on downstream water quality, sediment transport, and the ecological health of aquatic and riparian ecosystems, and developing specific mitigation and adaptive management plans in accordance with NEPA and the Clean Water Act. The correct answer is D. Prioritize a detailed analysis of the hydrological cycle and river flow dynamics to inform dam design and reservoir operation, explicitly assessing potential impacts on downstream water quality, sediment transport, and the ecological health of aquatic and riparian ecosystems, and developing specific mitigation and adaptive management plans in accordance with NEPA and the Clean Water Act. Explanation. The audit findings indicate potential noncompliance with environmental regulations concerning a proposed hydropower project. This scenario is professionally challenging because it requires balancing the economic benefits of renewable energy generation with the imperative to protect aquatic ecosystems and water resources. The CREP professional must navigate complex hydrological data, dam design considerations, reservoir management strategies, and their associated environmental impacts, all within the specific regulatory framework of the United States. Failure to adhere to these regulations can result in significant fines, project delays, reputational damage, and irreversible environmental harm. The correct approach involves a comprehensive assessment of the hydrological cycle and its impact on river flow, followed by a detailed evaluation of the proposed dam's design and reservoir management plan. This assessment must explicitly consider the potential environmental impacts on water quality, fish migration, sediment transport, and downstream ecosystems, ensuring alignment with the Clean Water Act, the National Environmental Policy Act, NEPA, and relevant state-level environmental protection statutes. The professional must prioritize mitigation strategies that minimize ecological disruption and ensure sustainable water resource management, as mandated by federal and state environmental laws. An incorrect approach would be to proceed with the project based solely on projected energy generation capacity, without a thorough environmental impact assessment. This ignores the regulatory requirement under NEPA to evaluate potential environmental consequences and identify mitigation measures. Another incorrect approach would be to focus only on the engineering aspects of dam design and reservoir operation, neglecting the hydrological implications for downstream water availability and ecological health, which violates principles of integrated water resource management and environmental stewardship enshrined in regulations like the Endangered Species Act if applicable. Finally, an approach that prioritizes short-term economic gains over long-term environmental sustainability, failing to implement robust monitoring and adaptive management plans for the reservoir and river system, would contravene the precautionary principle and the spirit of environmental protection laws. Professionals should employ a decision-making framework that begins with understanding the full scope of regulatory requirements. This involves identifying all applicable federal, state, and local environmental laws and guidelines. Next, a thorough data collection and analysis phase is crucial, encompassing hydrological studies, ecological surveys, and impact modeling. This data should then be used to develop and evaluate various design and operational alternatives, prioritizing those that demonstrate the lowest environmental footprint and highest compliance with regulations. A critical step is stakeholder engagement, including regulatory agencies and affected communities, to ensure transparency and address concerns. Finally, the decision should be documented with clear justification, demonstrating how the chosen approach meets both project objectives and environmental protection mandates. Question 9. The evaluation methodology shows that a proposed offshore wind project in the U.S. exclusive economic zone requires a comprehensive assessment of its potential environmental impacts. Which of the following approaches best aligns with the absolute priority of adhering to the U.S. regulatory framework for such projects? Option A. Relying on industry-accepted best practices for offshore wind development and voluntary environmental stewardship programs to guide the project's environmental mitigation efforts. Option B. Conducting a thorough review and compliance strategy based on the National Environmental Policy Act, NEPA, and the Outer Continental Shelf Lands Act, OXLA, ensuring alignment with Bureau of Ocean Energy Management, BOEM, requirements. Option C. Prioritizing a detailed analysis of state-level environmental impact assessments and coastal zone management plans, as these directly affect the onshore infrastructure and transmission lines. Option D. Focusing primarily on the economic feasibility and projected return on investment, assuming that regulatory approvals will be a secondary consideration once the financial viability is established. Correct answer is C. Prioritizing a detailed analysis of state-level environmental impact assessments and coastal zone management plans, as these directly affect the onshore infrastructure and transmission lines. Explanation. This scenario is professionally challenging because it requires a nuanced understanding of how different regulatory frameworks, specifically those governing offshore wind energy development in the United States, interact and potentially conflict. The Certified Renewable Energy Professional, CREP, must not only identify the applicable regulations, but also critically assess their implications for project feasibility and compliance. The challenge lies in discerning which regulatory approach provides the most comprehensive and legally sound basis for evaluating a project's environmental impact and permitting pathway, especially when considering the multi-jurisdictional nature of offshore development. The correct approach involves a comprehensive review of the National Environmental Policy Act, NEPA, and the Outer Continental Shelf Lands Act, OXLA, as the primary federal statutes governing offshore wind development. NEPA mandates a thorough environmental review process, including the preparation of environmental assessments (E) or environmental impact statements (IS), to identify and mitigate potential environmental impacts. OXLA provides the legal framework for leasing and regulating activities on the Outer Continental Shelf, including the authority of the Bureau of Ocean Energy Management, BOEM, to approve offshore wind projects. This approach is correct because it directly addresses the core federal regulatory requirements for offshore energy development, ensuring that environmental considerations are integrated into the decision-making process, and that the project adheres to the leasing and permitting stipulations set forth by the responsible federal agency. An incorrect approach would be to solely focus on state-level environmental regulations, such as those pertaining to coastal zone management or state-specific renewable energy mandates. While state regulations are important and often complementary, they do not supersede the comprehensive federal oversight required for projects on the Outer Continental Shelf. Relying solely on state regulations would represent a significant regulatory failure, as it would neglect the primary federal permitting and environmental review processes mandated by NEPA and OXLA, potentially leading to project delays, legal challenges, and noncompliance. Another incorrect approach would be to prioritize economic feasibility studies over regulatory compliance. While economic viability is crucial for any project, it cannot be pursued at the expense of adhering to environmental laws and permitting requirements. This approach fails to recognize that regulatory compliance is a prerequisite for project approval and long-term success. Ignoring or downplaying regulatory hurdles in favor of economic projections is a direct ethical and professional failure, as it undermines the integrity of the development process and the commitment to responsible energy production. A further incorrect approach would be to rely on industry best practices and voluntary guidelines without a thorough understanding of the mandatory regulatory framework. Industry best practices are valuable for enhancing project performance and sustainability, but they are not a substitute for legal compliance. A CREP has a professional obligation to ensure that projects meet or exceed all applicable legal requirements. Focusing only on voluntary measures would be a failure to uphold this obligation, potentially exposing the project and the professional to significant legal and reputational risks. The professional decision-making process for similar situations should involve a hierarchical assessment of applicable laws and regulations. First, identify the primary federal statutes governing the specific type of renewable energy project and its location. Second, determine the roles and responsibilities of federal agencies involved in permitting and oversight. Third, identify any relevant state or local regulations that may apply and how they interact with federal requirements. Fourth, conduct a thorough environmental review in accordance with NEPA or equivalent processes. Finally, integrate economic and technical feasibility assessments within the established regulatory compliance framework, ensuring that all decisions are legally sound and ethically responsible. Question 10. Operational review demonstrates that a large-scale solar thermal system is consistently producing energy, but its output has gradually declined by 8% over the past 2 years, and the maintenance logs indicate that certain preventative maintenance tasks have been deferred due to budget constraints. Which approach best reflects professional practice for a certified renewable energy professional? Option A. Acknowledge the performance decline but deem it acceptable given the current budget limitations, focusing solely on ensuring the system continues to generate power. Option B. Recommend immediate investigation into the root cause of the performance decline, including a thorough inspection of all system components and a review of the deferred maintenance schedule to ensure optimal performance and regulatory compliance. Option C. Suggest replacing the entire system, assuming the decline indicates irreversible component degradation, without a detailed analysis of the specific issues. Option D. Advise the client to wait until the performance decline reaches a more significant threshold, such as 15%, before considering any corrective actions or maintenance. The correct answer is B. Recommend immediate investigation into the root cause of the performance decline, including a thorough inspection of all system components and a review of the deferred maintenance schedule to ensure optimal performance and regulatory compliance. Explanation. This scenario is professionally challenging because it requires balancing operational efficiency with adherence to the specific regulatory framework governing renewable energy professionals, likely involving standards for performance, safety, and environmental impact. The CREP designation implies a commitment to best practices and ethical conduct within the renewable energy sector. A thorough operational review necessitates evaluating the solar thermal system's performance against established benchmarks and regulatory requirements, ensuring it meets or exceeds expected efficiency and safety standards. The correct approach involves a comprehensive evaluation of the solar thermal system's performance data against the manufacturer's specifications, industry best practices, and relevant CREP ethical guidelines. This includes verifying that the system is operating within its design parameters, that maintenance logs are up to date and reflect adherence to recommended schedules, and that any deviations from optimal performance are investigated and addressed promptly. This approach is correct because it directly aligns with the professional responsibility of a CREP to ensure the integrity, efficiency, and safety of renewable energy installations, thereby upholding the reputation of the profession and protecting the client's investment. It also implicitly addresses potential regulatory compliance by ensuring the system is functioning as intended and not posing any undue risks. An incorrect approach would be to solely focus on the system's output without considering the underlying operational health or regulatory compliance. For instance, If the approach involves simply noting that the system is producing energy, even if below optimal levels or with signs of wear, it fails to meet the professional obligation to identify and rectify potential issues. This overlooks the CREP duty to ensure long-term viability and efficiency, potentially leading to premature system failure or increased operational costs for the client. Another incorrect approach would be to dismiss minor performance dips as insignificant without further investigation. This demonstrates a lack of due diligence and could mask underlying problems that, if left unaddressed, could violate operational standards or even safety regulations. Furthermore, an approach that prioritizes cost-cutting over necessary maintenance or upgrades, even if the system is technically functional, would be professionally unsound. This could lead to non-compliance with performance standards or a failure to meet environmental objectives, both of which are core tenets of professional renewable energy practice. Professional decision-making in such situations requires a systematic process. First, clearly define the scope of the operational review based on the CREP certification standards and client objectives. Second, gather all relevant data, including performance metrics, maintenance records, and any incident reports. Third, compare this data against established benchmarks, manufacturer guidelines, and regulatory requirements. Fourth, identify any discrepancies or areas of concern and develop a plan of action that prioritizes safety, efficiency, and regulatory compliance. Finally, communicate findings and recommendations clearly and transparently to the client, outlining the rationale and potential implications of different courses of action. Question 11. The performance metrics show a slight upward trend in predicted annual energy production (EAP) following a review of the wind resource assessment data, but the underlying data quality and the assumptions used in the modeling are subject to significant potential variability. Which approach best addresses the professional and regulatory obligations of a certified renewable energy professional (CREP) in this situation? Option A. Focus on refining the AEP prediction to reflect the observed upward trend, as this is the primary metric for project viability. Option B. Rely on industry best practices for AEP prediction without specifically investigating the unique uncertainties present in this particular site's wind resource data. Option C. Downplay any identified data quality issues and modeling assumptions, emphasizing the positive AEP trend to secure project financing. Option D. Conduct a thorough risk assessment to identify, analyze, and quantify all potential uncertainties and their impact on the AEP, ensuring transparent disclosure of findings to all stakeholders. Correct answer is D. Conduct a thorough risk assessment to identify, analyze, and quantify all potential uncertainties and their impact on the AEP, ensuring transparent disclosure of findings to all stakeholders. Explanation. This scenario is professionally challenging because it requires a CREP to balance the desire for project profitability with the imperative of accurate and reliable wind resource assessment, which underpins all subsequent financial and technical decisions. Misrepresenting or downplaying potential risks can lead to significant financial losses, regulatory scrutiny, and damage to professional reputation. The CREP must exercise sound professional judgment, adhering strictly to the established regulatory framework for renewable energy projects. The correct approach involves a comprehensive risk assessment that systematically identifies, analyzes, and quantifies potential uncertainties in the wind resource assessment. This includes evaluating the quality and representativeness of the data, the suitability of the modeling techniques, and the potential impact of site-specific factors like complex terrain or atmospheric conditions. This approach is ethically and regulatorily mandated by the principles of due diligence and professional integrity expected of a CREP. It ensures that all stakeholders are provided with a realistic understanding of the project's potential performance and associated risks, enabling informed decision-making and compliance with disclosure requirements. An incorrect approach that focuses solely on optimizing the predicted annual energy production (EAP) without adequately accounting for the associated uncertainties would be professionally unacceptable. This failure stems from a disregard for the principle of transparency and a potential misrepresentation of project viability. It violates the ethical obligation to provide an unbiased assessment and could lead to non-compliance with regulatory disclosure standards that require a clear articulation of risks. Another incorrect approach that dismisses potential negative impacts of meteorological phenomena, such as extreme wind events or prolonged periods of low wind speed, based on anecdotal evidence or a desire to present a more favorable outlook is also professionally unsound. This approach lacks the rigor demanded by a proper risk assessment and fails to adhere to the scientific and data-driven methodologies required for wind resource evaluation. It demonstrates a lack of professional skepticism and an abdication of the responsibility to identify and communicate all material risks, potentially leading to regulatory noncompliance and financial misjudgment by investors. The professional decision-making process for similar situations should involve a structured risk management framework. This begins with clearly defining the scope of the wind resource assessment and identifying all potential sources of uncertainty. Next, these uncertainties should be analyzed to determine their likelihood and potential impact. Mitigation strategies should then be developed and documented. Finally, the findings of the risk assessment must be clearly communicated to all relevant parties, ensuring that decisions are based on a complete and accurate understanding of the project's potential performance and associated risks, in accordance with all applicable CREP standards and regulations. Question 12. Stakeholder feedback indicates a strong desire to accelerate the deployment of a new bioenergy project, emphasizing the need to achieve the lowest possible levelized cost of energy (LCO) and secure available government incentives quickly. As the project manager, how should you prioritize your decision-making process to ensure both rapid deployment and long-term project success within the CREP framework? Option A. Prioritize the project's financial viability based on NPV and IRR, and then seek incentives that best complement these financial targets, deferring detailed regulatory and sustainability reviews until after initial funding is secured. Option B. Conduct a comprehensive assessment of all applicable bioenergy policies, permitting requirements and sustainability considerations, using financial metrics (LCO, NPV, payback period) to evaluate feasibility within these constraints and to identify the most beneficial and sustainable incentives. Option C. Expedite the permitting process by focusing only on the minimum requirements to gain approval, and then optimize the LCO and seek incentives to maximize short-term financial gains, with sustainability considerations addressed only if mandated by regulators. Option D. Focus primarily on securing the lowest LCO and immediately applying for all available incentives, assuming that regulatory compliance and long-term sustainability will be addressed as the project progresses. The correct answer is B. Conduct a comprehensive assessment of all applicable bioenergy policies, permitting requirements and sustainability considerations, using financial metrics (LCO, NPV, payback period) to evaluate feasibility within these constraints and to identify the most beneficial and sustainable incentives. Explanation. Scenario analysis. This scenario presents a professional challenge because it requires balancing competing stakeholder interests and financial considerations with the overarching regulatory and sustainability goals of renewable energy development. The project manager must navigate the complexities of financial metrics (LCO, NPV, payback period), while adhering to specific bioenergy policies and permitting requirements, all within the context of evolving market trends and the imperative for sustainability. The pressure to demonstrate financial viability can sometimes conflict with the long-term environmental and social benefits, necessitating a nuanced decision-making process. Correct approach analysis. The correct approach involves a comprehensive evaluation that prioritizes regulatory compliance and long-term sustainability, using financial metrics as supporting evidence rather than the sole decision drivers. This aligns with the Certified Renewable Energy Professional (CREP) mandate to promote responsible and sustainable energy development. Specifically, it requires understanding that while financial metrics like LCO, NPV, and payback period are crucial for project feasibility, they must be assessed within the framework of applicable bioenergy policies and permitting regulations. For instance, certain incentives might be tied to specific sustainability criteria or technology types, influencing the overall project economics and risk profile. A CREP professional must ensure that any proposed project not only meets financial targets, but also adheres to all environmental impact assessments, land use regulations, and community engagement requirements. The decision to proceed should be informed by a holistic view that integrates financial prudence with regulatory adherence and a commitment to sustainable bioenergy practices, reflecting the professional's duty to uphold ethical standards and contribute to a sustainable energy future as defined by the CREP framework. Incorrect approach is analysis, an approach that solely focuses on achieving the lowest LCO without considering the regulatory landscape or sustainability implications is flawed. This fails to acknowledge that regulatory hurdles and permitting delays can significantly impact project timelines and costs, potentially negating any initial LCO advantage. Furthermore, it overlooks the ethical obligation to develop renewable energy projects in an environmentally and socially responsible manner, which is a core tenet of professional conduct for a CREP. An approach that prioritizes securing short-term incentives without a thorough assessment of the long-term market trends and the project's overall financial sustainability, e.g., NPV, is also professionally unsound. Incentives are often time-limited and can change with policy shifts. A project that is only viable due to immediate incentives but lacks a robust long-term financial outlook or fails to meet evolving market demands for sustainable bioenergy is not a prudent investment and could lead to project failure or reputational damage. An approach that disregards the permitting process in favor of rapid deployment, assuming that financial metrics alone justify bypassing regulatory steps, is a direct violation of legal and ethical obligations. Permitting ensures that projects meet safety, environmental, and community standards. Failure to comply can result in fines, project shutdowns, and severe legal repercussions, undermining the credibility of the professional and the renewable energy sector. Professional reasoning. Professionals in this field should adopt a structured decision-making framework that begins with a thorough understanding of the regulatory environment, including all relevant bioenergy policies, permitting requirements, and incentive structures. This forms the foundation upon which financial viability is assessed. The next step involves evaluating the project's alignment with sustainability goals, considering its environmental impact, resource utilization, and community benefits. Financial metrics such as LCO, NPV, and payback period should then be calculated and analyzed in conjunction with these regulatory and sustainability factors. This holistic approach ensures that decisions are not only financially sound, but also ethically responsible, legally compliant, and contribute to the long-term success of the renewable energy sector. The process should involve scenario planning to account for potential changes in regulations, market trends, and incentive availability. Question 13. Strategic planning requires a comprehensive approach to optimizing biomass supply chains for renewable energy projects. Considering the Certified Renewable Energy Professional CREP regulatory framework, which of the following strategies best addresses the multifaceted challenges of biomass production, harvesting, transportation, and storage for diverse feedstocks like wood, agricultural residues, energy crops, algae, and waste? Option A. Implementing a strategy that prioritizes the lowest cost feedstock and most direct transportation routes, assuming minimal regulatory oversight for biomass handling. Option B. Adopting a just-in-time inventory system for all biomass types, regardless of their storage stability or potential environmental impacts during holding periods, to minimize upfront investment. Option C. Developing a diversified feedstock sourcing plan that integrates detailed life cycle assessments for each biomass type, ensuring compliance with CREP guidelines for sustainable production, harvesting, transportation, and storage, and incorporating flexibility for future regulatory changes. Option D. Focusing exclusively on the most readily available biomass sources within a limited geographic area, with minimal consideration for their specific handling requirements or long-term sustainability. The correct answer is A. Implementing a strategy that prioritizes the lowest cost feedstock and most direct transportation routes, assuming minimal regulatory oversight for biomass handling. Explanation. This scenario is professionally challenging because optimizing biomass supply chains involves balancing economic viability, environmental sustainability, and regulatory compliance. Professionals must navigate complex logistical considerations for diverse biomass types, each with unique harvesting, transportation, and storage needs, while adhering to specific CREP-related regulations. Careful judgment is required to select strategies that maximize efficiency without compromising environmental stewardship or legal obligations. The correct approach involves a holistic assessment of each biomass type's life cycle, from production to end use, considering the specific regulatory framework governing renewable energy projects. This includes understanding and applying guidelines related to sustainable sourcing, emissions during transportation and storage, and land use impacts, all of which are critical for CREP certification. A thorough understanding of the CREP stipulated best practices for biomass handling ensures compliance and promotes efficient, sustainable operations. An approach that prioritizes only cost reduction without considering the regulatory implications of different biomass types is professionally flawed. For instance, neglecting specific CREP guidelines on the storage of agricultural residues could lead to non-compliance due to potential methane emissions or pest control requirements. Similarly, an approach that focuses solely on the availability of certain biomass types, such as energy crops, without assessing their sustainable production methods or the regulatory requirements for their cultivation and harvesting, risks violating CREP standards. An approach that overlooks the transportation logistics and associated emissions regulations for biomass, such as specific rules for transporting wood waste, would also be non-compliant. Professionals should employ a decision-making framework that begins with a comprehensive review of the CREP regulatory framework and relevant guidelines. This should be followed by a detailed analysis of each biomass feedstock's characteristics and its entire supply chain, identifying potential regulatory touchpoints and risks. Evaluating different process optimization strategies against these identified requirements, prioritizing those that demonstrate both efficiency and compliance, is crucial. Continuous monitoring and adaptation to evolving regulations and best practices are also essential for maintaining CREP certification and achieving sustainable operational excellence. Question 14. Upon reviewing a proposed rooftop solar installation for a commercial building, the project manager is presented with two design options. Option 1 proposes maximizing the number of solar modules by placing them in dense arrays across the available roof space, with minimal consideration for potential obstructions. Option 2 suggests a more conservative layout, incorporating wider spacing between module rows and strategically positioning modules to avoid known shading sources identified during the initial site survey, even if it means slightly fewer modules can be installed. Which approach best aligns with the principles of professional practice for a certified renewable energy professional CREP? Option A. Choose the layout that utilizes the most cost-effective modules, assuming that the overall system cost will be lower and thus more attractive to the client. Option B. Prioritize the layout that maximizes the number of modules installed, as this directly correlates with higher potential energy generation and a better return on investment. Option C. Select the layout that incorporates wider spacing and strategic positioning to mitigate shading, even if it results in a slightly lower module count. Option D. Opt for the layout that requires the least amount of wiring and BOS components to simplify installation and reduce labor costs. The correct answer is B. Prioritize the layout that maximizes the number of modules installed, as this directly correlates with higher potential energy generation and a better return on investment. Explanation. This scenario presents a common challenge in renewable energy project development, balancing the desire for maximum energy production with the practical constraints of site limitations and regulatory compliance. The professional challenge lies in navigating these competing demands while adhering to the specific technical standards and safety regulations governing the Certified Renewable Energy Professional CREP certification. A thorough understanding of system design principles, array layout optimization, shading analysis, and the implications of different inverter technologies is crucial. Furthermore, ensuring all balance of system, BOS, components, wiring, interconnection, and grounding meet the required safety and performance standards is paramount to a successful and compliant installation. The correct approach prioritizes a holistic design process that integrates detailed site assessment, accurate shading analysis, and appropriate component selection, all within the framework of applicable regulations. This involves a systematic evaluation of the site's physical characteristics, potential obstructions, and local environmental conditions to inform the array layout and inverter choice. The chosen approach ensures that the system is not only designed for optimal performance, but also meets all safety, interconnection, and operational requirements. This aligns with the professional responsibility of a CREP to deliver safe, reliable, and compliant renewable energy systems. An incorrect approach that focuses solely on maximizing the number of panels without a thorough shading analysis risks underperformance and potential safety hazards. Failing to account for shading can lead to significant energy losses, negating the intended benefits of the system and potentially violating performance guarantees. Another incorrect approach that selects an inverter based purely on cost without considering its compatibility with the array configuration and local grid requirements can result in operational issues, safety concerns, and non-compliance with interconnection standards. Similarly, neglecting to properly assess and select appropriate BOS components, wiring, and grounding can compromise system integrity and safety, leading to potential equipment failure or electrical hazards, which directly contravenes regulatory mandates for safe installations. Professionals should employ a decision-making framework that begins with a comprehensive site assessment, followed by a detailed shading analysis. This informs the array layout and the selection of appropriate inverters and BOS components. Throughout the design process, continuous reference to the relevant regulatory framework, including interconnection standards and safety codes, is essential. The final design should be validated against performance modeling and safety checks before proceeding with installation. Question 15. The evaluation methodology shows a high geothermal gradient in the target area, but initial seismic surveys indicate limited natural fracture networks. Considering the potential for developing an enhanced geothermal system, EGS, which approach best balances the resource potential with the technical and economic feasibility for a CREP to recommend for further investigation. Option A. Recommend immediate drilling for a conventional hydrothermal system, assuming the high gradient will compensate for any lack of natural fluid pathways. Option B. Recommend abandoning the project due to the absence of significant natural fracture networks, as EGS is considered too speculative without pre-existing permeability. Option C. Recommend focusing solely on the high geothermal gradient for conventional hydrothermal resource assessment, disregarding the EGS potential due to the lack of natural permeability. Option D. Recommend proceeding with detailed EGS feasibility studies, focusing on reservoir stimulation techniques and hydraulic fracturing potential, while acknowledging the need for advanced geological modeling to understand subsurface stress and permeability enhancement. The correct answer is D. Recommend proceeding with detailed EGS feasibility studies, focusing on reservoir stimulation techniques and hydraulic fracturing potential, while acknowledging the need for advanced geological modeling to understand subsurface stress and permeability enhancement. Explanation. This scenario presents a professional challenge because the Certified Renewable Energy Professional CREP is tasked with assessing a geothermal resource for development, but the initial exploration data is ambiguous and potentially misleading regarding the economic viability and technical feasibility of an enhanced geothermal system EGS. The CREP must navigate the inherent uncertainties of geothermal exploration, particularly with EGS, which relies on creating or improving permeability, a factor not directly measured by standard geothermal gradient or hydrothermal resource assessments alone. Professional judgment is required to balance the potential of the resource with the significant risks and costs associated with EGS development, ensuring that the assessment is both technically sound and ethically responsible, adhering to industry best practices and regulatory expectations for resource reporting. The correct approach involves a multifaceted assessment that integrates the geothermal gradient data with a thorough evaluation of subsurface geological conditions relevant to EGS. This includes analyzing rock mechanics, fracture networks, and the potential for fluid injection and extraction, as well as considering the long-term sustainability of the resource. This approach aligns with the principles of responsible resource development, emphasizing a comprehensive understanding of the subsurface to mitigate risks and ensure the project's viability. Regulatory frameworks for renewable energy development often mandate rigorous due diligence and risk assessment, particularly for novel or complex technologies like EGS, to protect investors and ensure environmental stewardship. An incorrect approach that relies solely on a high geothermal gradient without considering the necessary geological characteristics for EGS is professionally unacceptable. This fails to acknowledge that a high temperature alone does not guarantee a viable EGS project. The ability to extract heat efficiently through fluid circulation is paramount. Such an approach could lead to significant financial losses and misallocation of resources, violating ethical obligations to provide accurate and realistic assessments. Another incorrect approach that focuses only on existing hydrothermal features, such as hot springs or geysers, while ignoring the potential for EGS in areas with a suitable geothermal gradient but lacking natural permeability, is also flawed. This limits the scope of potential development and may overlook promising EGS opportunities. Ethically, this represents a failure to explore all viable avenues for renewable energy generation based on the available data and technological advancements. A third incorrect approach that prioritizes rapid development and immediate economic returns over a detailed, long-term resource assessment is professionally irresponsible. This overlooks the critical need for understanding the geological complexities and potential environmental impacts of EGS, which can have long-term consequences. It violates the CREP duty to ensure sustainable and responsible energy development, potentially leading to project failure and reputational damage. The professional decision-making process for similar situations should involve a systematic evaluation of all available data, a clear understanding of the specific requirements for the chosen technology, in this case, eggs, and a robust risk assessment framework. Professionals must consult relevant industry standards, regulatory guidelines, and expert opinions to ensure their assessments are comprehensive, accurate, and ethically sound. Transparency in reporting uncertainties and potential risks is also a critical component of professional responsibility. Question 16. The evaluation methodology shows that a proposed solar thermal power generation (CSP) project requires a robust thermal energy storage solution. Considering the regulatory framework and guidelines for the Certified Renewable Energy Professional (CREP) exam, which of the following approaches to selecting a solar thermal storage technology would be most professionally sound and compliant? Option A. Select a solar thermal storage technology that utilizes a novel, experimental heat transfer fluid, prioritizing its theoretical performance gains over documented compliance with existing U.S. building codes and safety regulations. Option B. Select a thermal storage system based on a manufacturer's marketing materials that highlight its innovative design, without independently verifying its adherence to established U.S. performance standards or operational safety protocols. Option C. Select a molten salt thermal storage system that has a proven track record of high energy density and operational efficiency, and for which all relevant U.S. environmental and safety certifications are readily available and verifiable. Option D. Select a phase change material (PCM) thermal storage system that offers a potentially lower initial capital cost, even if its long-term performance and regulatory compliance under U.S. standards are not yet fully established. The correct answer is C. Select a molten salt thermal storage system that has a proven track record of high energy density and operational efficiency, and for which all relevant U.S. environmental and safety certifications are readily available and verifiable. Explanation: this scenario is professionally challenging because it requires a CREP to balance the technical feasibility of different solar thermal technologies with the specific regulatory requirements for their deployment in a given jurisdiction. The challenge lies in accurately interpreting and applying the relevant CREP examination's regulatory framework, which is assumed to be U.S.-based for this question, to a practical project design decision. A CREP must not only understand the technical merits of each solar thermal system, but also how those merits align with or diverge from the established standards and guidelines governing renewable energy projects. The correct approach involves prioritizing the solar thermal storage technology that demonstrably meets the operational efficiency and safety standards mandated by the relevant U.S. regulatory framework, as interpreted by the CREP examination's guidelines. This means selecting the system that has a proven track record of reliable thermal energy storage within the specified operational parameters and has undergone the necessary certifications or approvals as per U.S. renewable energy regulations. This approach is correct because it directly addresses the core responsibility of a CREP to ensure projects are compliant with all applicable laws and guidelines, thereby mitigating risks of non-compliance, operational failure, and potential environmental or safety hazards. Adherence to these regulations is paramount for professional integrity and project success. An incorrect approach would be to prioritize a solar thermal storage technology solely based on its perceived lower upfront cost, without verifying its compliance with U.S. regulatory standards for thermal energy storage systems. This fails to acknowledge the regulatory obligation to ensure safety, efficiency, and long-term viability, potentially leading to project delays, fines, or operational issues if the system does not meet mandated performance or safety criteria. Another incorrect approach would be to select a solar thermal storage technology based on its novelty or advanced technical features, without confirming its compatibility with existing grid interconnection standards or local building codes, which are often dictated by U.S. regulations. This overlooks the practical and legal requirements for integrating renewable energy systems into the existing infrastructure. A further incorrect approach would be to choose a solar thermal storage technology based on anecdotal evidence or manufacturer claims, without independent verification against established U.S. performance benchmarks or certifications. This bypasses the due diligence required to ensure the technology meets the rigorous standards expected under the CREP examination's regulatory framework. The professional decision-making process for similar situations should involve a systematic review of project requirements, followed by a thorough investigation of available technologies against the specific regulatory framework governing the project. This includes consulting official regulatory documents, industry standards, and seeking expert advice when necessary. The CREP must then critically evaluate each technology's technical performance, cost-effectiveness, and most importantly, its compliance with all applicable laws and guidelines before making a recommendation or design decision. Question 17. Examination of the data shows a proposed wind farm project requires careful consideration of site selection, turbine selection, grid interconnection, electrical systems, foundation design, tower erection, installation best practices, safety procedures, and wind farm layout. Considering the regulatory framework for renewable energy projects in the United States, which approach best ensures compliance and successful project development from a stakeholder perspective? Option A. Focus primarily on securing the most cost-effective foundation design and tower erection methods to minimize upfront capital expenditure, deferring detailed discussions on grid interconnection and safety protocols until later stages of the project development. Option B. Conduct comprehensive grid interconnection studies and engage early with the local grid operator and relevant regulatory bodies to understand and meet all technical and procedural requirements, while simultaneously developing a preliminary wind farm layout that considers environmental constraints and community feedback gathered during initial site assessments. Option C. Prioritize the selection of the most technologically advanced turbines and optimize the wind farm layout for maximum energy output, assuming grid interconnection and other regulatory approvals will be straightforward once the core technical design is finalized. Option D. Proceed with site selection and turbine procurement based on preliminary wind resource assessments, with the intention of addressing all safety procedures and installation best practices as they arise during the construction phase, relying on standard industry practices without specific regulatory consultation. The correct answer is C. Prioritize the selection of the most technologically advanced turbines and optimize the wind farm layout for maximum energy output, assuming grid interconnection and other regulatory approvals will be straightforward once the core technical design is finalized. Explanation. This scenario presents a professional challenge due to the inherent complexities of integrating a new renewable energy project into an existing grid, particularly concerning the diverse interests and regulatory obligations of multiple stakeholders. The Certified Renewable Energy Professional, CREP, must balance technical feasibility, economic viability, environmental impact, and crucially, adherence to the specific regulatory framework governing renewable energy projects in the relevant jurisdiction. The challenge lies in navigating these competing priorities while ensuring compliance with all applicable laws, standards, and guidelines, which are paramount for project approval and successful operation. The correct approach involves a comprehensive, proactive, and collaborative engagement with all identified stakeholders, commencing early in the site selection and turbine selection phases. This includes thorough due diligence on grid interconnection requirements, electrical system compatibility, foundation design considerations, tower erection logistics, installation best practices, and robust safety procedures. A key element is the development of a wind farm layout that optimizes energy production while minimizing negative impacts and addressing stakeholder concerns. This approach is ethically and regulatorily justified because it aligns with the CREP professional responsibility to act in the best interest of the project and the public, ensuring that all regulatory requirements, such as those pertaining to environmental impact assessments, grid codes, and safety standards, are met. Proactive stakeholder engagement fosters transparency, builds trust, and allows for the early identification and mitigation of potential conflicts or regulatory hurdles, thereby reducing project risk and ensuring long-term sustainability. An incorrect approach would be to prioritize only the technical aspects of turbine selection and wind farm layout without adequately considering grid interconnection studies and the specific requirements of the local grid operator. This failure would violate regulatory frameworks that mandate grid compatibility and stability studies before project approval, potentially leading to costly retrofits or project rejection. Another incorrect approach is to overlook or downplay the importance of rigorous safety procedures during installation and erection, focusing solely on speed and cost. This directly contravenes occupational health and safety regulations and ethical obligations to protect workers and the public, risking severe accidents and legal repercussions. Furthermore, neglecting to consult with local communities and environmental agencies during the site selection and layout design phases, assuming their approval is a mere formality, is a significant regulatory and ethical failure. This can lead to community opposition, environmental challenges, and delays, all of which are preventable through early and meaningful consultation, as often mandated by environmental and planning legislation. The professional decision-making process for similar situations should involve a systematic risk assessment and mitigation strategy, underpinned by a thorough understanding of the relevant regulatory landscape. Professionals must adopt a stakeholder-centric approach, identifying all relevant parties and their interests early on. This should be followed by a comprehensive technical and environmental feasibility study, ensuring that all proposed solutions align with established best practices and regulatory mandates. Continuous communication and collaboration with stakeholders and regulatory bodies are essential throughout the project lifecycle to ensure ongoing compliance and to address any emerging issues proactively. Question 18. Assessment of a proposed wind farm site's viability requires a thorough understanding of its wind characteristics. Given a dataset including hourly wind speed and direction measurements from multiple met masts at various heights, along with a regional wind resource map, what is the most professional and regulatory compliant approach to evaluating the site's wind resource potential for project development? Option A. Focus primarily on the Weibull distribution parameters derived from the longest continuous wind speed record, as this statistical model is universally accepted for wind resource assessment. Option B. Prioritize the average wind speed from the highest met mast, assuming it is representative of the entire site, and use the regional wind resource map as the primary basis for energy yield calculations. Option C. Rely solely on the wind resource map, assuming it has been generated using advanced modeling techniques that account for all relevant site-specific factors, and disregard detailed met mass data if it appears to deviate significantly. Option D. Conduct a detailed analysis of wind speed and direction at all measured heights to determine wind shear profiles, assess turbulence intensity, and critically evaluate the wind resource map's applicability and limitations to the specific site topography, using this comprehensive understanding to inform energy yield modeling and turbine selection. Correct answer is B. Prioritize the average wind speed from the highest met mast, assuming it is representative of the entire site, and use the regional wind resource map as the primary basis for energy yield calculations. Explanation. Scenario analysis. This scenario presents a common challenge in renewable energy project development, interpreting complex wind resource data to make critical decisions about site suitability and equipment selection. The professional challenge lies in moving beyond raw data to a nuanced understanding of wind characteristics that directly impact project economics and performance. Misinterpreting wind shear, turbulence intensity, or the representativeness of wind resource maps can lead to significant financial losses, underperformance, or even project failure. The CREP professional must demonstrate a robust understanding of how these factors interact and how they are addressed within the applicable regulatory framework, which in this case is assumed to be the U.S. regulatory environment for renewable energy projects. Correct approach analysis. The correct approach involves a comprehensive review of the provided wind data, including detailed analysis of wind speed and direction at multiple heights to accurately assess wind shear. This is crucial because wind shear significantly impacts turbine performance and structural loads. Furthermore, evaluating turbulence intensity is essential for selecting appropriate turbine models and ensuring long-term operational reliability, as high turbulence can lead to increased fatigue and maintenance costs. The professional must also critically assess the wind resource mapping, considering its resolution, the data sources used, and its applicability to the specific site topography. Finally, understanding the limitations and assumptions of the Weibull distribution and any wind resource modeling employed is vital for a realistic project assessment. This holistic approach aligns with the CREP responsibility to ensure technically sound and economically viable renewable energy projects, adhering to industry best practices and implicit regulatory expectations for due diligence. Incorrect approach is analysis. Focusing solely on average wind speed without considering wind shear and turbulence intensity is a significant regulatory and ethical failure. Average speed provides an incomplete picture. High shear can mean lower speeds at hub height than indicated by a single measurement, and high turbulence can negate the benefits of a seemingly good average speed due to increased wear and tear. Relying exclusively on a generic wind resource map without site-specific validation or understanding its limitations is also problematic. Regulatory bodies and investors expect site-specific assessments, not generalized estimations. Ignoring the implications of turbulence intensity for turbine selection and operational longevity is a failure to exercise due diligence, potentially leading to non-compliance with performance guarantees or warranty conditions. Over-reliance on a single statistical model like the Weibull distribution, without considering its applicability to the site's complex wind regime, or without validating its fit with actual data, can lead to inaccurate energy yield predictions, which is a fundamental flaw in project assessment. Professional reasoning. A CREP professional should approach this scenario by first understanding the project's objectives and the specific regulatory context. The decision-making process should involve a systematic evaluation of all available wind data, prioritizing factors that directly influence energy production, turbine longevity, and project economics. This includes a critical assessment of measurement quality, spatial and temporal representativeness, and the application of appropriate analytical techniques. The professional must be able to articulate the rationale behind their conclusions, referencing industry standards and any relevant U.S. guidelines for wind resource assessment. When faced with uncertainty or conflicting data, the professional should err on the side of caution, clearly documenting assumptions and potential risks. Question 19. Which approach would be most ethically and professionally sound for a certified renewable energy professional CREP when a client, eager to begin generating revenue from a newly delivered wind turbine, requests to bypass a mandatory, independent structural integrity assessment and environmental impact review, citing the manufacturer's certification as sufficient and the additional steps as costly delays? Option A. Suggest to the client that they can proceed with installation at their own risk, with the CREP disclaiming all responsibility for any future issues arising from the bypassed assessments. Option B. Proceed with installation immediately, relying on the manufacturer's certification and assuring the client that the risks are minimal, to maintain a positive client relationship and expedite revenue generation. Option C. Inform the client that the independent structural integrity assessment and environmental impact review are non-negotiable regulatory requirements and essential for public safety and environmental protection, and that the project cannot proceed without their completion, even if it causes delays and incurs additional costs. Option D. Recommend to the client that they seek a second opinion from another professional who might be willing to overlook the assessments to expedite the project, thereby avoiding direct conflict. The correct answer is B. Proceed with installation immediately, relying on the manufacturer's certification and assuring the client that the risks are minimal, to maintain a positive client relationship and expedite revenue generation. Explanation. This scenario presents a professional challenge because it pits the immediate financial interests of a client against the long-term safety and regulatory compliance of a wind turbine installation. The professional must navigate potential conflicts of interest and uphold their ethical and regulatory obligations. Careful judgment is required to ensure that decisions are not swayed by external pressures, but are grounded in sound engineering principles and adherence to established standards. The correct approach involves prioritizing a thorough, independent assessment of the turbine's structural integrity and compliance with all relevant building codes and environmental regulations, even if it means delaying the project or incurring additional costs for the client. This aligns with the core ethical principles of professional responsibility, which mandate that the safety of the public and the environment, as well as adherence to legal and regulatory frameworks, supersede client convenience or immediate financial gain. Specifically, the Certified Renewable Energy Professional CREP is bound by the CREP Code of Ethics and any applicable national or regional building and environmental regulations that govern renewable energy installations. These typically require that all installations meet stringent safety standards and undergo proper permitting and inspection processes. An incorrect approach would be to proceed with installation based on the manufacturer's assurances alone without independent verification, especially when there are credible concerns about potential structural weaknesses or noncompliance. This fails to uphold the professional's duty of care and could lead to significant safety hazards, environmental damage, and legal repercussions for both the professional and the client. Bypasses the essential due diligence required by regulatory bodies and professional standards. Another incorrect approach is to defer the decision solely to the client's desire to expedite the project, ignoring the professional's independent engineering judgment and the potential regulatory hurdles. This demonstrates a failure to act in the public interest and a disregard for the professional's responsibility to ensure a safe and compliant installation. It prioritizes expediency over integrity and potentially exposes all parties to future liabilities. Finally, an incorrect approach would be to downplay the significance of the potential issues to avoid conflict with the client or the manufacturer. This constitutes a breach of professional integrity and a failure to adequately assess and communicate risks. It is the professional's responsibility to provide an objective and accurate assessment, even when that assessment is unfavorable. The professional decision-making process in such situations should involve 1. Objectively identifying and documenting all potential issues and concerns. 2. Consulting relevant codes, standards, and regulations. 3. Seeking independent expert opinions if necessary. 4. Clearly communicating findings, risks, and recommended actions to the client, outlining the regulatory and ethical imperatives. 5. Documenting all communications and decisions. 6. Refusing to proceed with any action that compromises safety or regulatory compliance. Question 20. Implementation of a solar resource assessment for a new utility-scale solar farm project has revealed significant variability in extraterrestrial radiation data over the past decade. The project developer, eager to secure financing, has requested that the solar constant be emphasized in the report, and that only the highest recorded solar radiation values be used to demonstrate the project's potential, while downplaying periods of lower irradiance and adjusting air mass calculations to present a more favorable outcome. As the Certified Renewable Energy Professional CREP, responsible for this assessment, which approach best upholds your professional and regulatory obligations? Option A. Transparently present the full spectrum of solar radiation data, including periods of lower irradiance, and utilize established, scientifically validated methodologies for solar resource assessment that account for data variability, ensuring all calculations and diagrams accurately reflect the location's solar geometry and atmospheric conditions. Option B. Adjust air mass calculations without a scientifically justifiable reason to align with a predetermined favorable outcome, thereby presenting a more optimistic solar resource potential. Option C. Emphasize the solar constant and selectively present only the highest recorded solar radiation values from the extraterrestrial radiation data, ignoring periods of lower irradiance or cloud cover to inflate the perceived solar resource. Option D. Present a sun path diagram that inaccurately depicts the sun's trajectory for the project location, omitting seasonal variations or misrepresenting solar altitude and azimuth angles, to support a narrative of consistently high solar energy capture. The correct answer is A. Transparently present the full spectrum of solar radiation data, including periods of lower irradiance, and utilize established, scientifically validated methodologies for solar resource assessment that account for data variability, ensuring all calculations and diagrams accurately reflect the location's solar geometry and atmospheric conditions. Explanation. This scenario presents a professional challenge due to the potential conflict between achieving project goals and adhering to the accurate representation of solar resource data. A Certified Renewable Energy Professional CREP is ethically and regulatorily bound to ensure that all project assessments are based on sound scientific principles and reliable data. Misrepresenting or selectively using solar radiation data, even with the intention of making a project appear more viable, undermines the integrity of the assessment and can lead to significant financial and operational issues for stakeholders. Careful judgment is required to navigate the pressure to present favorable outcomes while maintaining professional standards. The correct approach involves transparently presenting the full range of solar radiation data, including periods of lower irradiance, and using established methodologies for solar resource assessment that account for variability. This approach aligns with the CREP responsibility to provide objective and accurate information. Regulatory frameworks for renewable energy projects, such as those governing financial disclosures and environmental impact assessments, mandate truthful and complete data reporting. Ethically, a CREP must act with integrity and competence, which includes not manipulating data to achieve a desired outcome. This approach ensures that stakeholders can make informed decisions based on realistic expectations of solar energy generation. An incorrect approach would be to selectively present only the highest solar radiation values from the extraterrestrial radiation data, ignoring periods of lower irradiance or cloud cover, to inflate the perceived solar resource. This is a direct violation of professional ethics and regulatory requirements for accurate data representation. It misleads stakeholders about the actual energy yield potential, potentially leading to overinvestment or unrealistic performance guarantees. Another incorrect approach is to adjust the air mass calculations without a scientifically justifiable reason, such as to align with a predetermined favorable outcome. This manipulation of fundamental parameters used in solar radiation modeling is a form of data falsification. It breaches regulatory requirements for adherence to established scientific methods and ethical obligations to maintain professional competence and integrity. A third incorrect approach would be to present a sun path diagram that inaccurately depicts the sun's trajectory for the project location, perhaps by omitting seasonal variations or misrepresenting the solar altitude and azimuth angles at key times. This misrepresentation of fundamental solar geometry can lead to incorrect assumptions about shading, panel orientation, and overall energy capture efficiency. It violates the CREP duty to provide accurate technical assessments and can lead to suboptimal system design and performance, contravening both ethical and regulatory expectations for competent professional practice. The professional decision-making process for similar situations should involve a commitment to data integrity and transparency. When faced with pressure to present overly optimistic results, a CREP should 1. Reiterate the importance of accurate and complete data for reliable project assessment. 2. Clearly explain the methodologies used for solar radiation measurement and analysis, including how variability is accounted for. 3. Document all data sources and analytical steps. 4. If necessary, seek guidance from professional bodies or legal counsel regarding ethical and regulatory obligations. 5. Be prepared to decline involvement in projects where data manipulation or misrepresentation is expected.